I've got a new PCB, but in a shocking development for the channel, this one did not come from PCB Way. Is this the end of the PCB Way Atomic 14 relationship? Watch on to find out. I actually printed this PCB at home. These Volterra machines have been around for a couple of years now, and I finally got my hands on one to do some prototyping. The printer uses conductive silver ink to lay down the tracks and pads. It's pretty mesmerising to watch, but I'm going to speed it up a bit for this video. I will upload the complete print sequence as a separate video on the Extras channel for you to watch. Once the board has been printed, we need to cure the ink by baking it. This is what it looks like under the microscope before it's been baked. It looks kind of like someone has squeezed some marshmallows onto the PCB. After baking, it looks much flatter, and to my eye, it also looks shinier. We're now ready to assemble the board, but I have jumped ahead over a whole bunch of steps. So let's rewind a bit and have a look at the PCB layout and design. We've got some limitations on what we can do. In theory, with the Volterra, you can do double-sided boards. There is a drill attachment, and you can create the equivalent of vias and plated through holes using small rivets. I don't have the drill attachment, and to be honest, I think trying to line up both sides of the board would be pretty difficult. So the first limitation is that I can only do single-sided boards. To be honest, this does lead to a few routing issues, but people managed with single-sided boards for a long time before PCB manufacturing became super cheap. The other limitation is that the bonding between the conductive ink and the board is not that strong. Here's the previous version, and I managed to snap off the header quite easily. So instead of trying to use a surface mount USB socket, which would put a lot of strain on the connection as you plug and unplug it, I have used a breakout board and one of these vertical surface mount sockets. I may try a direct USB connection in the future just to see how robust it is, but I'm not holding out much hope. The minimum trace width is 8mm or 0.2mm, and we've also got a minimum pin pitch of 0.65mm for SMT IC packages, and 0603 is the smallest component size we can use. There's also no silkscreen or solder resist, and we have to use lead-free low-temperature solder. Those are the only real limitations we have, but they are pretty big limitations. So to answer the question at the start of the video, the Atomic 14 PCB Way partnership is still on. We're still going to need to use them for most of our boards. In fact, they are just finishing up a board for me now with SMD assembly on both sides. I'm really looking forward to getting my hands on them. For this initial test, I've made my traces all 0.4mm wide. This results in 2 passes of conductive ink. For a lot of the connections, I could have probably used thinner traces and just had 1 pass, but I decided to play it safe. The circuit is very simple. It's just an ESP32 S3 module, a voltage regulator to take the 5 volts from USB down to 3.3 volts, and some LEDs so we can see the board working. There's a bit of prep work to do before we can actually print. The first thing to do is position the circuit. The software shows us where it's going to draw the PCB by moving the probe around the outline of the circuit. We can then adjust the position to match where we've clamped the board. With our circuit located, we then need to probe the height of the board. This needs to be really accurate, so it probes a lot of points. For my board, this took around 3 minutes. With our height map measured, we can start to print. The first step is a quick calibration of the ink printing. I've attached the conductive ink, and we print out a test pattern to make sure we get good results. With my setup, I didn't need to tweak any of the settings, so we can just wipe off the ink and print the PCB. This generally wipes off without any problems, but you can use a bit of isopropyl alcohol if needed. We've already seen the printing stage of the process, so I'll speed it up to make it super fast. As I say, I'll upload a normal speed version of this to the Extras channel. Baking the conductive ink takes around 20 minutes, and once it's cured and the machine has cooled down, we're ready to dispense the solder paste. The first thing we need to do is get everything aligned again. The software identifies a pad on the circuit, and we manually position the probe at the centre of that pad. We then get given another pad, and we repeat the process. These 2 points are enough for the software to know where all the pads are on the board, and we can easily sanity check this by making it go to various positions on the board and checking that it does actually reach the right pads. Dispensing the solder paste is really quick. It takes just under 3 minutes from my design, and I have quite a few pads for the ESP32's module. I'm always fascinated by what solder paste looks like under the microscope. Tiny balls of solder suspended in flux. It's amazing technology. Now, my alignment was not perfect, but that doesn't really matter that much. We've got solder paste on the pads. Placing the components is all pretty straightforward, though I am wondering now if a pick and place machine is the next thing to add to the home workshop. We've got the various decoupling capacitors along with the RC circuit for the enable pin. The voltage regulator is pretty easy as it's such a big component, and the two buttons are also very simple. For the LEDs, we just need to make sure we get the orientation of these correct. For the ones I'm using, green end is the cathode or negative. And we've got the matching current limiting resistors. I've gone for fairly arbitrary 510 ohms, which will give us around 6 mA for each LED. We've got our vertically mounted SMD header. I quite like this one as it has pins on both sides, which should give us a nice strong connection to the board. And finally, the last component is the ESP32S3 module. This is so large I can just do it by hand and gently nudge it into position. Reflow takes around 20 minutes. The solder does behave slightly differently from what you'd normally see, as it doesn't really flow on the conductive ink pads, but it does make a solid electrical connection between the component pins and the pads, so that's pretty good. Looking at the joints under the microscope, it all seems to have worked nicely. It is really interesting to see how different this is from normal PCBs, where the solder really wets the pads and pins. I might tweak the footprints for the buttons in the future to make a more solid connection. Now, of course, you've seen this working at the start of the video, but when I recorded this, I had no idea if this would work. So the first thing I always do is check that I actually get a USB device showing up when I plug the board in. And I do! Fantastic! So the next check is, can I actually program it? I got a very basic sketch that will cycle through the LEDs, and it uploads without any problems. Our LEDs work nicely, cycling through the blue, green and red. We can even get the serial output working. It's pretty neat. Now, if you're observant, you'll have seen something interesting during programming. When the board is in firmware download mode, the red and green LEDs are both powered on. This is the real benefit of being able to quickly prototype things. I've used GPIO 39 for green and GPIO 40 for red. These are both used by the JTAG interface, and this seems to have some funny behaviour in download mode. I think I'm going to find this new tool a really nice addition to my workshop. Well, thanks for watching. If you want to learn more about ESP32S3 schematics, then the playlist highlighted right now is for you.